Today we're going to discuss section 3.6, which is Introduction to Functions. And let me say that functions are going to be throughout your entire mathematical career. So this is a very important section. So make sure that you understand everything, and please let me know if you have questions. I have posted the PowerPoint with the notes on as you learn. And there's also a guided notes, and it says Relations and Functions guided notes, or it says 3.6 guided notes, one of the two. But it's there for you if you'd like to pull it up and fill it in as we go along. But I thought what I'd do is just kind of run through the PowerPoint, and you can see where to put things over here in the guided notes. So we'll start with the PowerPoint, and the first thing that they want to talk about is identifying relations, domains, and ranges. So here's some vocabulary, and notice that the guided notes section starts with a vocabulary section. So we have that an equation with two variables defines a relation between two variables. So we're saying, okay, they've got some kind of relationship, and we can find that by inputting x's and getting out y values. A relation can be represented by an ordered pair, and it can also be represented by different types, so like graphs, see that here, tables, and mappings. And so we're going to talk about each one of those. The book actually doesn't even present mappings, but I thought that it would be a good idea for you to go ahead and see it. So we will do an example. And then when we talk about the domain, we are talking about all of the x-coordinates in the ordered pairs. And the range is all of the y values that we can get out if we input those x values. So in this next little section, the relation representations, you can do this example that's right here. And you can simply just record all of your. So in this next section, what I would like for you to do is try to represent this relation, which is given by these ordered pairs right here, in 4 different ways. So you can write in your ordered pairs right here in this column. Then I want you to graph each one of the ordered pairs. Then just write them in a table, and then we'll talk about a mapping. So I'll give you just a minute to do that. And if you want to, just touch the screen and press pause and go ahead and try it, and then we will pull up the mapping and the answers to the others. So with a mapping, what we want to do is we want to think about all of the things that we input, and so that's the same thing as all of our x-coordinates, which are in our domain. So if we think about our first one, we've got 4, and it maps to 7. And then we would put in a -4, and it maps to 7 as well. And then you could continue on. I don't have enough room in this one, but if you look on the next slide, here's all of the answers, so you can check your work and make sure you're good to go. So those are different ways to represent a relation. And then we can list our domain and our range down here by simply writing it in these little curly Q brackets, which is the way that we define kind of set notation, and all of the things that are in our domain, and then all of the things that are in our range. So just simply list each of your elements. Notice that there's 4 elements in our domain, but only 3 in our range, and that's because both 4 and -4 map to the 7. So our next objective is to identify functions. And so we have some vocabulary here, and that's given here on this first slide. And it tells us that a function is a special type of relation where if we have an x value, an element of the domain, then it maps to exactly 1 y value. And so it can't map to 2, it can't map to 3, it only has 1 y value for every single x. Or not for every single x, but for every x in the domain, there's only 1 y value associated with it. So what you can check for is that the domain values do not repeat. If they do, then you do not have a function. So you're looking to see if your x values repeat. And so if they do, then it's not a function. So looking back at our example from before, if we look at these ordered pairs, we're looking to see if the x's repeat. And if they do, then it's not a function. And so we look at 4, -4, 2, and 0. None of those repeat. So yeah, this is a function. A good note here is that it's okay for the y value to repeat, like the 7 did up here. It's just not okay for the x to repeat. So if we're given ordered pairs, we should check to make sure that the x's do not repeat. But if we're given a graph, then we want to test our graph with the vertical line test. Remember that when we graphed vertical lines, we said, okay, if we have x is equal to 2, then that means I make my t-chart and I say, okay, x always has to be equal to 2 no matter what. So I get y values of -1, 0, and 1. And so if I graph that guy, remember I go 1, 2, up or down 1, 1, 2, up and down 0, and then 1, 2, up and down 1. And so we get this vertical x is equal to graph. And so notice that my x's are repeating. And if you have 2 points on the graph of a vertical line that have the same x value but different y's, then this is not a function. Okay? So, we can always test this with the vertical line test. And so what we're going to look at are some examples to kind of help us do that. I think these two questions are pretty straightforward, but in case you're wondering what this value or this blank right here and this blank right here are, I'll go ahead and fill those in. The vertical line test states if a vertical line can be drawn so that it intersects a graph more than once, then the graph is not. Oops. A graph of a function. If no such vertical line can be drawn, then the graph is a function. I did note here that instead of drawing an actual vertical line in the graph, you can simply just lay your pencil down vertically on your graph and move it left to right, or move it slowly from the left to the right. And then when you do that, if the graph drawn on the paper intersects your pen more than one time on that vertical line, then it is not a function. Below that hint are some examples that I'd like you to try. Lay your pencil down vertically on each of these three graphs and see if they are functions by saying, hey, does this graph intersect my pencil more than one time? And then I'll show you the answers. So we see on this first one that yes, this is a function, because even if I move to the left and to the right, a vertical line is only going to get intersected by this blue line one time. The second one also is a function, because no matter what, if I move that vertical line, that red one, along that blue one, it's only ever going to intersect each other one time. However, this last one is not a function, because if I just put my pencil right here, then it is only intersecting it one time. But as I move to the right, I end up intersecting it here and here. And so these two would have the same x value and different y values. Notice that both of the first examples were lines. We had a graph of one that didn't have, or had a normal slope of 3 or 2 or 1/2. And then we had one of those special cases where we had a y is equal to, where we had 0 slope on that one. And when we think about lines are only ever going to be intersected by a vertical line test one time, except for in the case of these x is equal to statements, because we know that those produce vertical lines, and so therefore it's not going to pass the vertical line test. But otherwise, all linear equations are functions except for these right here. Take just a second to determine if each of the equations given there are functions. So you can pause the video, and then when you get done, you can come back and check your work, which I'm going to show on the next slide. So we have that the first one is definitely a function. It's a linear graph. The second one is also a linear graph, and we know that because we look at the x and the y, and we look at the exponents on each of those, and we notice that x is to the first power and y is to the first power. Therefore, this is a linear equation. And then the y is equal to statement is also a linear equation, and it's not an x equal to, so it is a function. However, the very last one is a line, but it's a vertical line and therefore does not pass the vertical line test, and so it is not a function. If we were to look at ordered pairs of it, the x's would repeat, and therefore it's not a function. This very last objective is to write equations using function notation, and this is the super important part. Yes, I want you to be able to identify functions, but being able to write them and understand what they mean in function notation is essential, because you guys will see function notation only in the future. Since in a function the x's are unique in that they're not going to repeat and they will produce different y's, they can produce the same y, but they're each going to be unique from other x's. That's what allows us to say that x is the independent variable, and y depends on whatever x value you plug into the function, and it will output your y values, which are dependent on the x. We often use the f, g, and h to name our different functions, and oftentimes if there's multiple functions on a graph, then they will use f and then g and then h all together. But most of the time, the most common one is f, and we read it, the symbol f parentheses x parentheses means the function of x, or we call it f of x. This is not to be confused with f times x, okay? Notice that the x or the f is in italics. It's not it's not a number that we're multiplying by. It's simply just a way to write y in a different way. So we're saying that the output of our function is based off of x. And so that's how we use that f of x notation. It says we're going to plug something in for x, and we have a function that is going to do something to x. In this case, we're going to multiply by -3 and then add 2. And that will produce a y value. Notice that the f of x and the y are in the exact same spot because they're both outputs. And here's what I just said in the slides. Another notation you might see is this f of 2 statement. And what this says is we want to plug in 2 for our x value, because remember that this originally was f of x right here. And so we're saying I want to plug in 2 where the x was. And so we are evaluating for 2, or when x is equal to 2, and we get a value out, and that is what f of x is equal to. It's the same thing as what y is equal to. On this example, which is also over here on your guided notes, and do note that my formatting didn't stay the same, so this is supposed to be an x squared. So what we want to do is we want to first write this linear equation in function notation. And so we're simply going to replace the y with an f of x. So we're going to say f of x is equal to x squared minus 2x. Now we have replaced our output value with an f of x, saying that this thing, whatever we have over here on the right, is a function of x, and we can input any independent x into this equation, and we will get out some value for our y, or our function. The next question asks us to find g of, and this is supposed to be f, or it could be g, I guess, so this one should be g right here instead of f. But we want to evaluate the function at -3, and so I do that here, but you can check your own work. All we're simply saying is I'm going to plug in a -3 wherever I see x. So this was originally an x squared, and this was minus 2x. Now, do be careful. make sure that you put things in parentheses when you square them, because -3 squared, if you plug that into your calculator and you plug in this into your calculator, it's going to give you two different answers. So always when you evaluate, use those parentheses. What you should get out is 15, and then we end up, you can find g of 0 and g of 2 as well for practice. So what you should get out for g of 0 is 0, and you should get out the same thing for 2. I do want to note that if you graph this guy, you get, we had a -3 that we plugged in for our x, and then we went all the way up to 15. I'm on a guesstimate. And then we had that it went through 0, 0, because this point right here is the same thing as 0, 0. And then we have the point 2, 0. So we go over here to 1, 2, and we put a little point. Now, you might not be able to tell what this looks like until you put a g of 1. And if you do that, what you'll end up with is a -1. And what we get is this graph right here that is parabolic in shape. And so you will see those more and more. And on this one, I shouldn't have actually connected all of these because this was supposed to be our discrete example. And what I mean by that is I have picked you out 3 x's or 3 things in your domain. So you could fill that in now. We could say -3, 0, and 2. And that is our domain. Those are the only x values that we evaluated. And then you can tell me what y's correspond with it. And that would be your range. But what I should have done is not connected all of these because this is supposed to be a discrete example where we just have certain x and what x values actually produce. And they are individual points. Now, if it wasn't a discrete example, then you could connect them and it would be parabolic. So I think that the domain and the range are not hard when you have discrete examples where you have specific x's that you're evaluating for, and you can simply just list each of those ordered pairs into that set notation. A lot of students struggle, though, with domain and range once we get to continuous functions. And so I have put here the slide that has information on domain and range, and I have put you guys some boxes over here to fill in for the domain and range, some questions to ask about each one of those. So take just a minute to record these questions right here, and then these questions right here, because those will be so important once you get to pre-calculus. You'll have to be able to identify the domain and range, and that is oftentimes where students struggle. So you want to think about, for your domain, are there any things that I can't plug in for my x value? Is there anything that would give me an undefined or would make the function kind of skip a spot or whatever? You want to think about, is there anything that you cannot do? So you want to think about if you had fractions. We know that there cannot be a 0 in the denominator. So if you have a fraction, check to make sure what x values are going to make that happen, have a 0 on the bottom. If there are any x values that make that happen, then that is a restriction on the domain. If you have, say, a square root, we know that square roots, you can't put negatives underneath them. If you do, taking the square root of it will produce an imaginary number. So that's what I mean by, are there any x values that are restricted? And then with our range, what you can think about is if I plug in all of my x's, what are the y values that I'm going to get out? Does it start at a certain point? Like if I had a graph that looked like this, here's the bottom of it. There's no graph down here anywhere. There's only it's starting at this. And so we think about what is that y equal to line, and we start there and then go to positive infinity. In the book, they only talk about the inequality notation. So looking at this column right here. So that's all you're required to know for this one. But I thought I'd go ahead and throw in the interval notation because we've already seen it. And we've talked about how if you have infinities or negative infinities, that negative infinity is going to be the smallest value, and it always gets a parentheses. And then positive infinity is going to be your biggest value, and it always gets a parentheses. Then we have talked about if it is less than or greater than, then it gets these parentheses here. And then if it is less than or equal to, or greater than, or less than or equal to, and greater than or equal to, sorry, I said those backwards, then they get the bracket that says, oh yeah, these are actually equivalent to that. So we've already talked about interval notation, so I thought I'd mention it. And this is more like what you guys will see in pre-calculus and in the future. This is graphing just one single variable on a number line. So what we're going to do is we're going to think about our x's and where they start, where the graph starts. If we kind of draw a vertical line at that x is equal to a statement, and where does it stop? So if I kept moving my x along the graph or along the x-axis with a vertical line, and I moved it along this way and this way, where is my graph, the original graph, kind of stopping? And if it keeps going forever, then we would have where it was going to positive infinity. We are also going to do this with the y as well, though. So we're not just restricted to one single dimension anymore. We are going to deal with both the x and the y. And so the x's will be our domain, and we'll write an inequality or an interval notation for our x. And then we will also write one for the y. Some things to note are that you might have to use a symbol that looks like this. It's called a union symbol. And I don't think I put it on your study guide, and so I wanted to make sure that I said something about it. So we'll do an example of the union statement, just so that you have what I'm talking about. And I'll erase this right here real quick. So if I had a graph that looked like this, and I had a little piece that started at -2 and went to -1, 0, so I've got this piece. And then I started one here and went to this piece up here, and so that's at 3, 2, okay? So if I have this right here, then I know I have a piece over here, and I have a piece over here. And what I want to do is I want to write my x values because I want to list my domain. So if I think about drawing a vertical line and moving it along the x-axis so that I'm thinking only about the x's, what is the first x that I encounter? Well, this one right here. And so we list that as, and because that is actually a point on the graph, we are going to list it with a bracket that says, okay, I'm going to start at x is equal to -2, and I'm going to move all the way up to this point right here, which was the x value of -1. And because that's actually a point, it's not got an open circle, we are going to use a bracket as well. But then we hop over. There's no graph in between here and here. It's simply just a kind of a gap. And the next x value that I encounter as I move along this x-axis is this one right here. And so we would need to use a union symbol here in order to say that we are jumping over a spot, and then we are picking back up at x is equal to 1. And then we keep moving along, and all the way up here to this very last one. That is x is equal to 3, and both of those are points, so we're going to use those brackets as indication of that. So now if I wanted to list my range, I'm thinking about moving along this y-axis. So I'm going to start down here at like -infinity, and I'm going to draw a horizontal line, or think about a horizontal line, and move this way up my axis and say, what is the very first y value that I encounter? Well, both of these sit on the x-axis, and we know that the x-axis, if we intercept the x-axis, then we have a y value out of 0. And so that's the very first point that we encounter. We keep moving up, we keep moving this dotted line up, and still hitting the graph right here, still hitting the graph right here, and this is our final one. So this point and this point are our final y values that we get out when we think about our range, and so that is the point 2 on our y-axis. And so it is included because it's actually a point on the graph. What I mean by that is if you encountered something that looked like this, where we had an open circle and then it went on, then we would say that is not actually included in it. And so we would use a parentheses there for that one. So on this next part, I have some examples for you in the guided notes. I want you to first evaluate the function at x is equal to 4. All you're doing is looking at the actual graph and you're saying, okay, where, if I plug in a x value of 4, so I go 1, 2, 3, 4 to the right, what is the y value that I get out? Well, this point right here, and so we get that y is equal to -4. So we get equal to -4. And instead of saying y is equal to, let's get in the habit of saying the function evaluated at 4, or f of 4, is equal to -4. The next part asks you to find the domain and range. And do note that on this one, it is a continuous graph because we are looking from this point all the way down to this point. And so it hits every single x and every single y in between those, which is different than our discrete problem from above where we had just individual points and they weren't connected and they didn't hit everything in between. So you're going to list your domain and your range, and you can just use inequality notation, but if you want to give yourself a challenge, go ahead and list it in interval notation as well. So if we think about our domain, it's all of our x's. So think about where we start on the graph and where we end, thinking about this x-axis. So if we're moving along here, what's the first x value that we encounter? Well, -3. And so we would have -3, and it is a point on the graph. It's got an actual point. So it is included, so we want to use brackets if we were doing interval notation. If you are doing the inequality notation, you're thinking about what's my first x value that I encounter? Well, it's going to be one of these form, where we're starting at -3, but we're less than or equal to that, and then less than or equal to, we stop at this x value right here. And so we'd have 1, 2, 3, 4, and we would be between those two values. You try the range, and so you're thinking about when you move along the y-axis and you start down here at the bottom and you start moving up, what's the first y value that you encounter and what's the last? Take just a second and try that, and you can pause the video, and then what I'll do now is I'll erase it so that you can see the answer. So you should have gotten -4 is less than or equal to x, which is less than or equal to 2. If you wanted to write it in interval notation, you would simply write -4, which is included, comma 2, which is included. So we're going all the way from y values of -4 all the way up to 2, and then we stop, but it's included. On the next example, you have to evaluate for g of 0 first. So look at your graph here, the second one, okay, and evaluate, find what is our output when we input an x value of 0. This next one, though, is a little different. Notice that this one is asking for, it tells us that g of x is equal to 3, and we want to find the x that does this. So you're thinking about, I want to know what x value can I plug in to get out a y value of 3. Well, if I think about drawing in a horizontal line, because we know that we're thinking about our y's, and we're saying, okay, we want to evaluate and eventually end up with a y value equal to 3. So if I go up here and go 1, 2, 3 on this, and I draw maybe a horizontal line in here, oh, there's actually 2 different x's that when I evaluate them, when I plug them into the function, they give me out a y value of 3. So it's this one right here and this one right here. And you can simply approximate. So we've got one of the x values is going to be -1. You can find the other. Then you want to state the domain and range. And so go ahead and try that now. I'm going to scroll up now so that you can check your work. So you should get that the domain, I can plug anything in for x. Notice that if I draw in a vertical line here, eventually this graph is going to intersect it. And I could move it all the way along this x-axis, and no matter what, I'm always going to get something out for that x value. I'm always going to be able to plug something in to get out a value, and it doesn't matter. There's not any holes in it. It doesn't stop, it doesn't terminate. It's one of these continuous ones that just keeps going forever because we have these little arrows on the end. Then if we want to think about the range is all, we're moving along this y-axis, and so we draw that horizontal line down here, and we say, okay, if I start moving it up, what's the first y value that I encounter? And that occurs right here, but then it never stops. It keeps going after that. And that's why we have y is greater than or equal to -2. If we were writing it in set notation, it would be -2 because that's where I start and it's included. And then we want to go all the way up to positive infinity. And infinity symbols always get parentheses. And that's the end of the PowerPoint. I do have a couple of examples over here for you to try. You can write the following in function notation and then determine if each of these relations are functions as well or if they're just relations. And then this is actually, I didn't mean for that to be in there. That was the answer to the one above. So you're all done.